So I'll talk about overall framework of stochastic optimization, where it fits, and then I'll go through this one example that's in this book I have with Francois Duval, which illustrates the issues that stochastic programming deals with. So things of like the value of information. And what I like to talk about is the value of the model. That having a stochastic programming model has value relative to a model that is totally deterministic. So what's the value of the model or the value of the stochastic solution? Okay, so those are the main points I'll cover in this lecture. Okay, so stochastic optimization and stochastic programming. All right, so each of them deals with, well, they deal with decision making under uncertainty. And you can almost always put them in this kind of form, that there's an expectation of some function, and we want to make a decision x. And so x is the decision, and there's some set of random outcomes, and that's represented here by c. And you want to make that decision such that you minimize or maximize the expectation of this function. Okay, so this fits into a lot of different areas. So that's so this in and of itself, this is you can think of stochastic optimization. What stochastic programming focuses on is where you have a lot of possible decisions. So so some areas focus on just discovering what, maybe you don't know exactly what f is, or you don't know what the distribution of c is. So some areas focus on those. Stochastic programming, we generally assume that we can somehow describe the distribution of the random parameters c. And we at least know how to represent the objective. So we have often a continuous, or at least a large range of decisions. So there are many possible decisions. So that's why we're using optimization. We're using techniques from optimization. The dimension, generally I say high dimension, meaning that in contrast to something like stochastic control, where you're usually trying to look at problems in 1 or 2 dimensions, stochastic programming deals with maybe 100-dimensional kind of decisions, or thousands, or even millions. So it has high dimension, and that's one thing that sort of separates it from other things. Oh, I see. Okay. Oh, maybe my. Okay. Let's see if the power is on. Okay, so so it could be in high dimensions, and then something else that, as I said, that often separates stochastic programming from other things. We know what the distribution is, or we can assume what the distribution is. This is in contrast to something like robust optimization, where you assume there are different distributions, or that you don't know the distribution. You don't know what it might possibly take on. So in stochastic programming, we often have that we know the distribution. It's a high dimension, a large range of decisions. And I think one thing that's maybe well, at least separates it from decision analysis is that their use of numerical optimization. So we are going to use that the number of decisions is sufficiently large that it's not, that we can't enumerate the set of possible decisions. So we have to use some kind of technique, numerical technique often, to find what the best possible decisions are. Okay. All right, so our basic model is that we're choosing a decision, and we want to optimize the expectation with respect here. I've just made a different random variable here, W, as opposed to C. So we want to optimize expectation with respect to some random variable of some function. And the types of questions, well, the types of questions in modeling are what should this function be? What should you put into that objective? So your model is talking about, how do I represent the outcomes? How do I evaluate the outcomes? So how do I come up with this, the representation of the objective function? One thing that Joydeep had mentioned, that my advisor was George Danzig. So one thing, often people would say to George Danzig, well, the simplex method must have been your greatest contribution, the simplex method for linear programming. And he said, well, no, actually, I think my greatest contribution was the objective function. The objective function. And so what he meant by it was that previous to his work, that people were just defining rules and following rules. And you would define a rule and follow it. And the goal of that would be to have something work. But what he did was to say, but what do you want it to do? And let's start with what it is that you wanted to do. And let's have a concrete way to represent what it is you want to do. So the objective function, he said, was his greatest contribution. Okay, so that's an important part of stochastic programming, is what is the objective function? How do you define what that objective function should be? So how to represent the loss, or how to represent utility from the decisions that you make. And then how to find that. What is it that you need to be able to describe that function, and how is it that you can go about doing that? Okay, so many of the questions in terms of models are associated with the objective function. So I think of everything kind of starts with the objective function, and then how do you use that objective function to find a solution? Okay, now within this, we describe stochastic programming models in multiple ways. One is the set of possible decisions. I think probably what is that, yeah, it's whether this is. What? Oh, okay. Yeah, I'm just wondering if it's not plugged in, but okay. Okay, so it could be two or multiple stages. Now, so two stages often means recourse. That is, that you make your decision, and then you see there's some realization of the uncertainty. And then if you get to act afterwards, that's called recourse. So if you have recourse, that would be after the action of these random variables. That separates out as part of stochastic programs. Often, there are stochastic programs that have reliability constraints or probabilistic constraints or chance constraints. All those have the same meaning. That's just another category. And then, as I said, robust optimization you could think of as part of stochastic programming as well. But this is where we don't really know the distribution. We're saying the distribution is just within some set, or the random variables just lie within some set. Okay, so again, stochastic programming focuses on many possible decisions, some form of mathematical optimization to make the choices, and actions that take place over time. They evolve sequentially over time as the uncertainty is revealed. And generally speaking, most of the time in stochastic programming, we talk about discrete points in time. So in other words, not continuous time. I'll mention some things in continuous time, but most of stochastic programming basically just refers to discrete time. So we just have a discrete event, we make a decision, we get some observations, then we may make more decisions and continue. Okay, so that's the basic setup of this. Now, what I'm going to do is I'll talk about these different possible or different descriptions of stochastic optimization that have come from different fields. So statistical decision theory, which goes back sort of to the mid-20th century, so statistical decision theory and decision analysis, they're mostly focused on gathering information. That is, they're mostly focused on there's some uncertain value or uncertain distribution that I'd like to discover. I don't know. I don't know how much oil is in the ground. I have to dig a test well in order to find out how much oil is in the ground. And decision analysis then refers to whether you should dig that well or not. But it's about discovering something, about trying to find out, to gather some information. So the focus there is about, well, I know that I have to make this action, but most of the focus is about, well, I would know how to make that action if I could understand what the uncertain parameters are. And the part of making the action is sort of obvious if I know what the parameters are. So if I know that there's oil in the ground, then I know that I should dig a well. But I don't know that there's oil in the ground, so I have to design some experiment to find out whether there's oil in the ground. And so you're trying to design the experiment in order to discover that. Okay, so that's kind of the focus of statistical decision theory. I would say machine learning, which is kind of the most, let's say the most prominent stochastic optimization framework now. So machine learning is, again, about discovering relationships, about trying to find out how to categorize people, whether they're, are they going to buy something or not. So that's also focused on information. Now, the pattern in machine learning is generally that we have lots and lots of data, many observations, but also many, many or very, very high dimensional features of those observations. So that's kind of I would say it's sort of a particular form of statistical decision theory where you're trying to understand how do these features relate to some classification or some categorization. How do those features relate to that? And what you want to do is to minimize the error. So the objective function is like the error or the loss from making a poor decision on classification, on whether somebody is going to buy something or somebody is not going to buy something. Okay, so that's machine learning. Now, dynamic programming is, I often think of it as kind of a particular version of stochastic programming, or like a part of it. In particular, it deals with dynamic problems, so problems where there's a sequence of decisions that you make over time. And often where the dimension of the decisions you make is usually small. So it's usually that there's a small set of decisions that have to be made, but you're making them sequentially over time, and you may be observing things about the environment over time. Many times that environment has a Markov process underneath it, so they become Markov decision processes. But this I think of as kind of a particular part of stochastic programs, and again, not emphasizing that there's a lot of actions to take, or that there's a high dimensional set of actions or high dimensional state space. So most of the time in dynamic programming, if the state space is too large, then we kind of break down. And most of the time in dynamic programming, you don't use or you don't take advantage of some of the properties like convexity that we try to take advantage of in stochastic programming. Another related area would be stochastic control. Now, stochastic control, generally, we think of that as being continuous in time, so sort of simple models, very low dimension, like 1, 2. So usually low dimension, continuous in time, but the same format that we're optimizing expectation of some function of our decisions and some random outcomes. So the same thing then. It has the same framework, that is, it's stochastic optimization, but the focus is on discovering properties of solutions generally in continuous time. And robust optimization, which you could think of as stochastic programming, where there's a particular kind of objective function associated with not knowing or being uncertain about the distributions, about the random parameters, the values that they might take on, or what distribution they might have. Okay, so so I have a little bit here to kind of to summarize that. So decision analysis is focused on lower dimension. One part of decision analysis is also that it's usually Bayesian, that is, you're usually applying Bayes' rule to update your information. So that is, you may do an experiment, like a test well, and then you update your probability of whether there's oil. So the Bayesian decision would be, I do some experiment, I have a prior probability of that there's oil in the ground, I do an experiment. From the result of that experiment, I'd update what that probability is. There is a lot of emphasis in decision analysis on the objective, or the form of the utility, and then how that utility responds to the uncertain parameters. But as I say, it's usually the action is somewhat obvious if I knew what the true underlying parameters were. So as I said, stochastic control, generally very low dimension, not so flexible. That is, usually you're trying to fit into a particular model that you can analyze. So often that means that you have to make a particular set of assumptions, like, oh, the dynamics are linear and plus some Gaussian noise. So you make some assumptions about the model so that you can actually do some analysis. But that means that it's not very flexible. That you're trying to force models into a particular, or you're trying to force the model to fit a particular form, whereas stochastic programming is it doesn't require any particular form. It's a general description, and you don't try to force things into particular forms like Gaussian linear dynamics and Gaussian noise. And the emphasis is on analytical and structural results. Markov decision processes, that's sort of the part of dynamic programming. Similar to the control emphasis, but less on continuous time and more on range of decisions. And as I said, machine learning is mostly about trying to discover some pattern, trying to discover, yes, whether people will prefer some product to another, whether people prefer, like, movies, some movie to another. Trying to discover those kinds of patterns, but with high-dimensional data. Okay. So what I'm going to do to illustrate this is to talk about a particular example. And then to take this example, or to look at this example from each of those different viewpoints. So what I'll do is I'll go through and say, well, if I were looking at this problem from the lens of stochastic control or from the lens of machine learning, how would I approach the problem? And then how would I approach the problem if I were doing it from a stochastic programming lens? Okay, so here's the problem. So suppose we're marketing on the internet. And let's say we're going to buy an ad, and we want to put it somewhere on the web page. So we could put it at the banner on the top of the web page, or we could put it on the side of the web page. And if you start at the top banner has the highest price, and then if you go along the side, it's sort of descending in price as you go down, as you know the user would scroll down the page. So depending on the position that we place the ad, we'll spend a given amount to place it. So let's say, so this would be that my ad, let's say I want to put my ad on Facebook. Facebook, I guess nobody wants to put their ads on Facebook now, but let's say, so you want to put this ad on this web page, and you're going to, you know from prior history that if you wanted to place it in position I, you would have to, for customer J, you would have to pay this amount, Cij. Okay, so we want to place our ads, we want to provide it to these different customers. So we have customers arriving to the website, and we want to place the ad in a position for those customers. This is how much it will cost. Let's say we have a given budget, so our budget is B. And let's say we can identify something about the customers. So we know what domain they're in. We know what operating system they're using. We might have cookies on the machine, so we know something about, let's say, their prior purchasing behavior or their prior browsing behavior. So we have a lot of information about each of these customers. So those customers' information is represented by these characteristics. And those characteristics occur with certain probabilities. So there's a certain probability that customer has each of these characteristics. But we don't know. We don't know exactly what those customers' characteristics are, but this is our probability. And then there's a market size here that's given. So this is like, this would be the number of people that come to the website, number of people that use the website every day. So a customer with characteristics of this form, WJ, and let's say we have an app, and what we'd like is that the customer downloads our app. So our goal is, let's get the customer to download our app. So with a customer with these characteristics is going to download our app with a given probability. All right, so now you can start to see where the different fields are going to put different emphasis. So one of them might be emphasizing what's the probability. One of them might be emphasizing how much should I spend on each of these ads. Okay, so they download our app with a given probability, and then they'll bring in some revenue. So the revenue is associated with how likely they are to continue to use our app. Will they buy a premium subscription, or will they, how much revenue am I going to get from this customer over time? So I have both whether they download the app, whether they actually become engaged, and then the revenue is going to be associated with do they stay engaged? Like what you want is somebody downloads your app. If it's free, you want them to visit a lot because then you get, let's say you get more traffic, or you might be able to sell ads yourself. So that's the revenue that's associated with it. And now the decision that you would want to make is how much should you pay for a customer of this type? So for this customer that has this type, how much are you going to pay for them? Okay, so here's the stochastic program. So I'll start with the stochastic programming view. And we'll think of it in terms of two-stage stochastic programming. So the first stage decision is what do I buy? So I'm going to represent what I buy by a set of decisions, which are, this would be the placement positions, I, and the set of customer types, J. So I have, for each of the placement decisions and each of the customer types, do I buy or not? So I'm basically saying, okay, for each customer type, what position am I going to try to target for them? So if it's a customer that I think is really likely to buy my product and will bring in a lot of revenue, maybe I want to put my ad in the top position. If it's a customer who I think is relatively unlikely, maybe I'll put my ad in a lower position. Okay, so the first stage decision is what do I buy? And let's say I have to pick one position, and one of the positions could be just I don't place an ad at all. So one of the members of this set would represent, oh, I just don't buy anything for that customer. That's a customer that is not worth my while to advertise to. Okay, and now there's a set of random realizations. So we make a decision about where we place the ad, and then we think about, well, what's going to happen? Well, for each of these M customers who arrives on any given day, there's a random variable for what type of customer they actually are. And then for each of those customers, we have whether they actually download the app. So QIJ is the probability that's associated with them. And then do they download the app? And then what we could think of is in the second stage, I realize new customers. So the second stage decision is really just sort of an outcome of their behavior. But this would be the set of real customers who I actually sign up. But I have a constraint that says in that second stage, I have to meet my budget. So what that means is if I've already hit my budget, I'm not going to be able to bring in these customers. So once I get to my budget, then I'm not going to place any more ads, not going to get any more revenue. So the second stage decision is effectively saying, well, I decide where to place these ads. People are going to arrive. They're going to download my app or not. Every time I place an ad, I'm charged. As soon as I hit my budget, they're not going to, if I was using Facebook or Google, they're not going to place my ad anymore once I hit my budget. I tell Facebook or Google, this is my budget and this is what I want to buy. And as soon as I hit my budget, that's it. I'm not going to get any more. So the budget constraint is what's kind of determining what happens in that second stage. So once I hit the budget, then I'm done. Okay, so this is the way a stochastic programmer would look at this. So if you're a stochastic programmer designing how you would spend money in this ad campaign, this is the way you would set this up. And the formulation would look something like this. So it would be, what am I going to do? I'm going to maximize profit, but that's going to be like minimizing costs. So the revenue that I get is negative in this case. So at the very beginning, I sort of know how much I'm going to spend. I'm going to spend Cij times Xij for all these ads that get placed. I've got this constraint that says, okay, for every customer type J, I place an ad in one position, so I decide one of the positions to place it. So all of that sums up to 1. And then I have, okay, now this is that I've decided to place this ad in position I. This is whether a customer of type J, this is like the fraction of customers of type J who actually appear. I don't know the fraction of customers of type J who actually are going to appear. This is the number of customers who appear. I also don't know exactly the number of customers. I made it depend on omega here represents the random outcomes. So this omega is representing what's random in the future. So I have these customers that are arriving, the number of customers that I have, and then my revenue can't be any higher than the number of customers and then what position I put them in. And the whatever revenue I get, also this is saying whether I get revenue or not. So whether I get revenue or not from a customer also is no larger than the budget. So the total amount that I spent on this customer can be no higher than the budget. And so my decisions are 0 or 1, and then this is the customer, whether the customer buys or not, that's not negative. Okay, so this would be a way to set this up as a stochastic program. Now let's look at it from these other perspectives. So if we were to look at it from a statistical decision theory or decision analysis point of view, we would do something like this. We would say the customer types and then their purchases are in some sort of Bayesian family. That is, there's a set of parameters that I'm trying to discover. And those parameters here are indicated by theta. But I don't know what those parameters are. So I would say there's some characteristics like their likelihood of purchasing, their likelihood of remaining customers, their likelihood of becoming premium customers. All of that's within this set of parameters theta. Okay, so I have some belief about how likely it is that people are within these different categories represented by theta. And I've said the distribution over those thetas is described by some set of hyperparameters, which I've indicated here by alpha. And so I have a belief about this sort of base set of parameters theta conditioned on what these hyperparameters are. And then my distribution of, well, how much revenue do I think I'm going to get from a given customer is a function of, the probability of that is a function of those base parameters theta. And then I'd focus on what happens as people make purchases. So I wouldn't be assuming it from the beginning. I would be trying to discover what is that purchasing behavior. So the emphasis here would be on, I want to find out if I place it in position 1, how likely are they to buy? And if I never place it in position 1, I'll never discover that. So I may have to experiment. I may have to try position 1, position 2, position 3 in order to discover how much I'm going to earn from these customers. So the focus would be on that experimentation, trying to discover how much it's worth to put them in these, to have ads in these different positions. Okay, so I'd have these observations, and then from those observations I would update what I think those likelihoods are for each of those customers. So the decision there would really be on the experimentation. Now that's not, as I said, that's not the focus of stochastic programming, which is more on, given that I know what those, or given I have my best guess, I would just say, well, what's my best guess of what those parameters are? And then how am I going to allocate my resources? Whereas in statistical decision theory, decision analysis, the focus would be on, I don't know what those parameters are. And actually, most of them would assume, well, it's pretty obvious what I should do if I knew what those parameters are. So they wouldn't focus on how should I spend my money if I know what the parameters are, because the assumption is, that part is easy. But the hard part is to find out what those parameters are. So it's like they're looking at kind of different parts of the problem. So as I said, that's sort of a simple policy choice, whereas in stochastic programs focuses on that policy choice as opposed to the learning part. Okay, now if it was machine learning, it would kind of be the same sort of focus that I really want to predict buying behavior. I want to find out how many of these people are going to buy versus not. And what I want to do is to minimize the loss that would be associated with predicting incorrectly. Or you could think of it also as, suppose I knew what the, let's say I knew what those true parameters were, I want to minimize the regret relative, that is, if I knew what the true parameters where what would I have done? I want to minimize the regret relative to what that best possible thing would have been. And so that, I would say machine learning is more specific about, it's like a branch of statistical decision theory, but sort of more specific about the form of the model that you'll use to make these, and without making choices about the experiments, but what the form of the model that you use to make your predictions. I often assume that there's a function, we'll take those characteristics, and we'll just take some function of those characteristics and try to use that to predict the behavior, predict like the buying behavior. So I'll have some function, so it could be a linear function, but it could be something else. I'll have some function of these characteristics that I use, and that function could also be a neural net. I mean, so it could be, so deep learning could fit into this as well. It would be, what function of these characteristics am I going to define in order to come up with a prediction of what those might be? So the focus would be on sort of building that function. How do I discover what that, or how do I set the parameters of that function, tune that function to make those predictions on buying behavior. And often you would start with a set of decisions, and then you'll follow the same kind of process that we'll use in stochastic programming, like stochastic gradient would be one of the algorithms, would be to update that function. So you would make your set of decisions, make an observation, and then update what that function might be. So that would be the focus of machine learning. Now, if I were to look at it from the perspective of Markov decision processes, I would say, okay, there's a fixed number of time points that I have to make decisions. So that those fixed number of time points might be each of the times that a customer arrives at the website. And at each of those points in time, I make decisions about how I assign the ads. So I would look at it from the perspective of each customer's arrival, and then where do I place the ad? And what I would think about is, I would look at it as a process saying, how much money do I have left? So I would have a state which describes what's my remaining budget, and a state which might describe what the current set of conversion rates are, conversion rates being like their probabilities of buying. And so I would update the state based on my action, my observation. So I would take an action, observe, update. I'd find the probability that people would convert, and then I'd probably use some kind of approximation, because if there are 10,000 people a day who come to the website, so this would be a 10,000 period problem, and there would be all these number of different types of customers. That would be a huge problem to try to solve exactly. So I'd use some kind of approximate method, like approximate dynamic programming, or some procedure like upper confidence bands that are used in multi-arm bandit problems. But there would be some kind of approximation procedure. And the approximation procedure might have some characteristics like it's asymptotically optimal. That is, as the number of customers increases, on average, I'm going to get closer and closer to an optimal decision for each customer. So I'll try to come up with an algorithm that does that asymptotically as I increase the number of customers to infinity. So again, the emphasis is different. It's usually on these continuous problems, some approximation, And then often what happens if I take some sort of asymptotic result. Number of customers increases to infinity. Okay, so stochastic control would be more about that I try to do things continuously, as I say, continuously over time. So you'd have a rate of earning over time based on past observations. And I might try to vary that rate as a function of time and the remaining budget. So in other words, I would try to represent everything in a lower dimensional position. So I might have a given sort of a given process or a given way in which I distribute the ads, and this rate would just be like the intensity of following that. That is, I'm only going to distribute to the top X% of customers. So my decision, instead of being on each customer, I'll make a decision about where to place the ad. It's just going to be, I'm just going to place the ad for X% of the customers. And so X is the top X% of those customers are going to get ads at any, or are going to get my ad at any point in time. And then the decision would just be regulating how many of the customers I try to convert at any given point in time based on how much budget I have left. And then there might be areas in which I keep, let's say, to 10% of the customers. But then when I hit a boundary, these would be the areas of hysteresis where I don't change control. So then I'll hit a boundary and I'll say, okay, at that boundary I switch to 15%. At another boundary I switch to 5%. So I'll follow the same, let's say I'll follow that constant fraction, getting ads, until I hit one of these boundaries. And then at those boundaries I change my action. So it would all be about kind of taking this, simplifying it down to maybe a single dimension, and then trying to control, look at how things dynamically move continuously in time with respect to that single dimension. And then, yeah, when the process hits those boundaries, then making those changes. Okay, now, last one is robust optimization. So as I said, so robust optimization is assuming that I don't know anything about the distribution, but I want to protect myself against the worst possible outcome. So that comes from control, where we don't know, maybe we don't know exactly what environment, like I'm flying a plane and I don't know what kind of conditions it's going to be in. I want it to be able to respond to all those conditions. So the same sort of thing would happen here with robust optimization, that I have this uncertain set of outcomes and I just prepare for the worst case in that uncertain set. So the highest cost that I would see out of purchasing these ads and then realizing some revenues from them, where the outcomes of those customer types and number of customers, where that varies. So it could be that, well, usually what happens when you have these worst case kind of things is this would be let's say the least likely customers to buy, and the fewest of them show up, and therefore I get the lowest kind of revenue. And then I'll plan for, well, where am I going to buy if the worst possible thing of those happens? Okay. All right. So those are different ways to look at stochastic programs. Now let me go through this example that to illustrate how stochastic programs work and what makes them different from deterministic programs. So now this problem, which is in my book with François Louveau, it's become sort of a pretty well known. So we put it in the book. The book was published in '97 originally, and then again in 2011. But this problem comes to me from all over the world. So I had people from Burkina Faso, somebody in the agricultural department, saying, well, we're planning our crop rotation for next year, and we're looking at your problem in your book. So can you tell us how to plan the crop rotation? So it's gone around all over the place, and I've seen people present it in talks in front of me without realizing that it was in the book. So we'll describe it here. So here's the situation. We have a farmer who's deciding how to plant this land. Now this is a European farmer. So we have corn, we have beets, and we have wheat. And the farmer has a bunch of livestock. So some of the crop has to go to the livestock. And some of the crops, like the beets, are just sold in the market. And the farmer is deciding, okay, how am I going to plant this land of 500 acres? How's the farmer going to plant that, divided up among these different crops? Okay, so the farmer knows that how much the livestock are going to consume, and thinks, well, I have to give, for the cows and the chickens, I have to have 200 tons of wheat and 240 tons of corn. And if I don't, well, if I don't exactly meet the requirement, so if I don't just feed the livestock, then if I have more, I can sell it on the market. But if I'm under, then I have to buy from the market. So if I have more than enough, then when I sell it on the market, I get like a low price. I get a wholesale price. But if I buy from the market, I have to buy at a retail price. So I buy at a higher price. So depending on whether I'm selling or buying, I have different prices. So that's one of the things in stochastic programming, that we represent specifically things like this, where there's one price to sell, one price to buy, and they're different. Yes. For livestock, yeah. If they don't make it themselves. Yeah. So if they don't have enough of their own production, then they'll buy from the market. And if they have more than enough, then they'll sell in the market. Right. Yeah. They'll sell at wholesale, but they'll have to buy at retail. Yeah. So they sell at the wholesale price and buy at retail. And now, so this is where the European part comes in. So in Europe, there's quotas on sugar beets. So every farmer gets a certain quota, and if you produce more than your quota, then you have to sell your beets to the government, and the government pays less than the market. So if you go above, and agriculture, I mean, even in the U.S., there are quotas on different crops. So this quota is, this farmer can only produce 6,000 tons. So the 6,000 tons of sugar beets is the most that the farmer can sell in the market. And beyond that, they have to sell to the government, but the government will only pay $10 a ton. So the first 6,000 tons gets $36 a ton, but beyond that, it's only $10 a ton. Okay, now, each of the crops has a different price for planting. So wheat is 150 an acre, corn is 230 an acre, and beets are 260. And on average, there are these yields. So these are average yields, or mean yields. So the wheat, 2.5 tons an acre, corn, 3 tons an acre, and sugar beets, it's a heavy crop, 20 tons an acre. But these are just means. So that's, of course, any farmer knows that you never get the mean. You'll always get more or less. But the mean is just an expectation. All right, now, if the farmer plans with just pure expectations, then the farmer would solve this problem. So I've set it up again as a minimization problem. So I minimize this is the cost for planting. And now this is the cost for meeting the livestock requirement and selling on the market. So we have 500, so we use up all the 500 acres. So X1, X2, X3 is how much we plant of each crop. And then here's my wheat requirement. If I'm below on the wheat requirement, then I have to buy in the market. If I'm above, then I can sell. So this was the price to buy, price to sell. Same thing for corn. And then for sugar beets, this is the amount that I sell on the market, and this is the amount that I sell to the government. And then the market amount is constrained by the quota. Okay, so this is a linear program. It's a linear program. There are 5 constraints here, non-negative variables. So 5 constraints, non-negative variables means there are 5 basic variables for an optimal solution. So any optimal solution is going to have 5 variables that are basic, or that, in other words, 5 variables that are going to be non-zero. Well, 3 of them are going to be the amount that I plant of each of these crops. So that means there's 2 more out of the set of variables here. So 2 more out of the next 4 are going to be non-zero. But that means that out of these 4 constraints, 2 of them have to be satisfied exactly. So two of these constraints has to be exactly met. Either I'm going to exactly produce my wheat, exactly produce my corn, or well, I'm also going to meet the B quota. Okay, so yeah, so V3's V3 is probably going to be at the maximum here. Well, yeah, I'm thinking about it in terms of if I were to write this as just a set of equations and non-negative variables, then there are just 5 equations, all non-negative variables, so 5-dimensional bases. So five things that could be non-zero out of this. 3 of them are going to be this, 2 others here, but that means that 2 of these have to be 0. And so that gives me that there are two of these sets of constraints that must be satisfied exactly. So in this optimal solution, I exactly satisfy the beet constraint, and I exactly meet the corn constraint. So those are the 2, and any set of conditions that I put on this, I'm always going to have 2 of these that comes out like that. Either I'll exactly meet the wheat and the corn, I'll exactly meet wheat and beets, or corn and beets like here, or I'll exactly meet wheat and beets. So in any deterministic solution, I'm always going to have that there are always going to be these two things that are satisfied exactly. Okay, now, what we want to do is to add uncertainty into this. So now, the farmer doesn't know what the yield's going to be, right? Because the weather, pests, seeds. So one thing the farmer might do is to try different scenarios and to see what would be best for each of the different scenarios. So to say, what happens in a high yield environment? What happens in a low yield environment? What happens in the average environment? Okay, so if I do this, I'll say, let's say the weather is the random factor. The weather can determine whether the yield is high or low. Let's say it's either plus or 20% of the mean. So if I have this scenario of an optimistic environment that is 20% higher, I get the same sort of behavior. I have exactly meeting corn, exactly meeting beets. That means I have, I have excess of wheat. This is how much I get in terms of wheat. That means I can sell more wheat on the market. In the pessimistic solution, where suppose that crop yield is actually 20% lower than the average, I still have this behavior that there are two sets of constraints that are met exactly, but now it's shifted. Before it was corn and beets, now it's wheat and beets. So I exactly meet the corn requirement, or I exactly meet the wheat requirement here, and exactly meet the beet requirement, but now I buy corn on the market. So before I was selling wheat on the market, here I'm buying corn on the market. This would average 167, this averages 60,000 a season. So the important thing is that each one of these solutions always has these two constraints that are met exactly. Okay, so as I said, because we have those 5 constraints, acreage, livestock need, and then the wheat quota, there are these 5 basic variables, 3 for the planting, 1 for the beets, and then one other one basically. We always have 1 for the beets. So the slack is either on the livestock, either I'm going to be over or under on one of those constraints. Okay, so a stochastic program puts all the decisions together. You say, suppose each of those scenarios were equally likely. So there's a probability of 1/3 to have each of those possible outcomes. And then in a single mathematical program, you maximize your expected profits or minimize negative expected profits. So again, you're solving a model that looks like this. I'm making decisions about X. Here's the number of acres that I plant. And I'm taking the expectation of those number of acres planted over the random variable, which here represents the yield of each of those crops. So the stochastic program would look like this. This, again, minimize the cost of planting. And now I add in the expected cost or negative profit of the crops after the season, which would be either I'm buying, like here, buying on the market, or selling on the market for each of those different crops. And now I have alternatives that depend on each of the possible outcomes in the future, each of the scenarios in the future. So that's that I in here. just use some shorthand to write down what the yields are. Yields depending on each of the i's. I is 1, 2, or 3. Okay, so and now here's the set of constraints. Okay, so this is what happens. Again, the decision maker, you plant the acres, nature picks the yield. The yield is high, medium, or low, and then you decide how much you buy or sell on the market. Those are the sequence of the decisions. Okay, now, what does the stochastic program solution look like? Well, there are 3 variables for the acreage. There are 6 variables associated with buying and selling. That is, for each of the scenarios for buying and selling. So for each scenario, there's either you buy or sell, or you're under and over on beats. So there were 6 of those for each of the buying and selling, but for each of the different possibilities. The constraints, there's 1 constraint for the acreage. There are 4 constraints in each scenario. So overall, that means I've got 18 variables. I have 13 constraints. That means I've got how many basic variables? 3 for the acreage, 3 for beats below yeah, let's say 3 for the acreage, 3 for beats. There are going to be 7 more variables or that are basic, or 2 in each scenario plus 1. The end result is there's still going to be 2 out of all those constraints. There's still 2 that won't have a slack variable that's positive. So there are 2 out of all those constraints that don't have a slack variable, the same as in the deterministic program. So I'll still end up, even though I have all those different scenarios, there are 2 spots where I'm going to exactly meet what the requirements are. What's different in the stochastic program, what I show here are how much you're planting of each of the crops, and this is the different scenarios for low, mean, and high yield. What's different is those 2 places where you have no slack on the constraint are in different scenarios. So in one scenario, I'm exactly meeting the corn requirement, but in a different scenario, I exactly meet the beet requirement. And this is a characteristic that no deterministic model can produce. This is the form of diversification which a stochastic program provides. So the characteristic of the problem is something that can't be reproduced. So often, sometimes people think, oh, if I just adjust a parameter in a deterministic model, if I adjust that parameter in some way, I'll be able to reproduce the stochastic solution. No, there's no way to just adjust a parameter in the deterministic model to reproduce the stochastic solution, because you can never get this kind of behavior where one tight constraint occurs in one scenario and another tight constraint occurs in a different scenario. So it's that kind of mixing or that kind of diversification that a stochastic program provides that a deterministic model can never provide. And that's kind of what separates stochastic programming solution from those others. So those 2 tight constraints are in different scenarios. That can never happen in a deterministic model. Now, with this solution, we can see different values of different parts of the model. So 1 is in the value of information. So the value of information is often expressed this way: the expected value of perfect information, which is what would it be worth to know ahead of time what the exact yield would be. So if you knew ahead of time what the yield would be, that would be like waiting and seeing. That's called the wait and see solution. I would wait to see what the outcome's going to be, see what it is, and then make my decision. If you were able to wait to see the yield, or if you knew the yield precisely, then you would get, on average, each of those best possible solutions for each of the different scenarios. So those were given before, this 167, 118, and 60. So that would give you 15,000. Now the difference between that and the stochastic solution up here is the value of information, or the expected value of perfect information. And that's the difference between this 115 and the 108. That 7,000 is the maximum that you would pay to learn the future precisely. So this is the maximum that a perfect forecast is worth. So if you're thinking about, well, I could gather more information about the weather, you would never pay more than $7,000, or you should never pay more than $7,000 for that information. Now, as I said, there's a difference in the stochastic solution relative to the deterministic solution, and that's captured by this: the value of the stochastic solution, which is this value up here, which I call the recourse problem, RP, and minus the expected value of using the solution with the means. Here I called it E-mean, EMS, E-mean solution, expected mean solution. So that difference, the expected mean solution, if I use the solution that was optimal just for the mean scenario, if I use that solution, I get 107 on average. The difference between that and the recourse problem here, that's the difference between this 108 and the 107, is 1150. This is the value of the model. This is just the value of putting it into a stochastic programming framework. Now, I have another example that will show this value could be higher than this value. That, in fact, this value could be large and this value could be small, or the other way around. This value could be large and this value could be small. But these both represent how much something is worth. This represents what's the value of just solving this model. This is just the value of having the model solution as opposed to solving the deterministic model. That's the deterministic model. EMS? Oh, EMS is the expected value of using the mean value solution. Yeah, without considering uncertainty. If I just use that solution, what would I get? So if you just use that solution ignoring uncertainty, you would get this, 107. Uh-huh. Oh, yeah. 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 Yes. Yeah, so this is the sum. This is, in each scenario, how much do I buy or sell of each of the crops? Yeah, A1I that's crop 1, scenario I. Crop 1, crop 2, and crop 3. You need to describe scenarios. You need to have a set of scenarios. Yeah, you need to have a set of scenarios. But often people say scenario analysis is an optimal decision for each scenario. But the optimal decision to this problem may be different from the optimal decision for any possible scenario.
Would it be that you take a solution for each of the optimal decisions along each of the scenarios, the problem, and then take an average? Would it be similar to this solution?
No, it can never be. It can never be. Yeah. Yeah. So those solutions, yeah, if you take the convex hull of the scenario solutions, it is just maybe disjoint from the optimal solution. In fact, it may even have different, there may be different variables that appear in the optimal solution than in that solution. Okay, so observations here. Two constraints are binding in the deterministic solution. The stochastic LP, there are still two constraints, but they're in different scenarios. So no single linear program can reproduce the stochastic program solution. So the stochastic program actually, it's including risk, it's including diversification, even though I didn't add in any risk aversion. It was just expected value. So stochastic programs apply even in cases where there's no risk aversion. And they end up doing diversification just because of this expected value. So you get diversification even though you didn't add risk aversion. Sometimes people think you need risk aversion to get diversification. In stochastic programs, you don't necessarily, because you have some nonlinear responses anyway in the problem. And you're just adjusting for it in your solutions. Okay, so this is just to give kind of a general framework. So we have, in the general stochastic program, you make decisions now. You observe. This is the recourse problem. You observe an uncertain outcome. I write it here, so I say, these are like the parameters C, but they depend on some generic random outcome omega. So C depends on this random outcome omega. And then you take an action that's in response to that. So it's a recourse action, Y of omega. And then the overall formulation is you minimize this first period costs, first stage costs, plus the expected value of what happens in that second stage. So this, because we realize it at the very beginning, this is known, and then this is the expectation of what happens in the second stage. And then your second stage problem, that's called your recourse problem. There might be some linear constraints. This is the linear program, two-stage stochastic linear program here. So this is the objective for the linear program. That's a transpose for the objective coefficients. You meet a set of linear constraints on X. Let's say equality constraints, non-negativity on X. And then the recourse problem is you minimize given your outcomes. Now, in this case, the uncertainty was all in here, in this, what we call the transformation matrix T. So T is transforming your decisions X into values in the future. And it's how do those planting decisions get transformed into the future? That's represented here by T. And I often use this script Q to represent that expected value. That's the recourse function. And here I had all the uncertainty in T, but we could have uncertainty in the H here, whatever goes in the right-hand side, or in the objective, or sometimes even in this W. Yeah, so,
Minimum of few transport
yeah,
second level. There doesn't seem to be
yeah,
any
that C is actually representing all these random parameters. Yeah, so C is the set of the random parameters. Here it's T. But it's C in general is anything that's random in here. Yeah, the recourse action. You had a question? Oh. Yeah, minimize over Y. Yeah, minimize over Y, and the C is actually it's the part of Q, W, H, and T that's random. It's the random part of those.
But you say that you observe an uncertain outcome. So is it that we have observed the psi and then we are trying to find the y here?
Yes, yeah. You observe. So here it would be you observe the yield, and now you decide the Y is how much you buy and sell. Yes, yeah. You could do this for any of the scenarios. Yeah. Okay, so this is, now, suppose the yields are just given with a distribution on every crop. So what I had before was, I just had those three values. But suppose there's a distribution over each of the yields. So the yields, let's say the yield is this little t here. It turns out if I could have any kind of continuous distribution over the yield, because once I plant each of the crops, then my decision is kind of made up at that point, because I'm either going to buy wheat on the market or sell it. I'm either going to buy corn or sell it. And I'm either going to sell all my beets, or I'm going to sell 6,000 tons and then buy or sell 6,000 tons to the market and the rest to the government. So what that means is that the value that I get from my decision in the future can be separated into each of these different crops. So I can separate into the value from, this would be crop 1, wheat, crop 2, corn, and crop 3, beets. I can separate it out into those three values. Each of those I can just find the expectation of. So I can find the expectation of how much I buy and sell of each of those crops. And that gives me that gives me the overall value of this function. So in other words, I could have continuous distribution for the crops. I didn't need to have three separate scenarios. What I'd have, even with a continuous distribution, though, is there would be two scenarios somewhere in that continuous distribution where I was exactly meeting the wheat requirement and exactly hitting the corn requirement. And just two of those, but occurring again in different scenarios. Now, when I do this, this is actually an example of the news vendor model, where the news vendor model is that a news vendor buys a set of newspapers at a cost. So in other words, each newspaper costs C. So the news vendor buys X papers at C and then sells them in the future at Q, and is allowed to return some of the unsold newspapers at a value R. But the demand is uncertain, and the news vendor has to decide, I'm missing some font here. This is supposed to be less than or equal to. So the news vendor is uncertain about the demand, and you can view this the same way. The news vendor spends, so I minimize C times X plus a recourse action. The recourse action is either I sell my newspapers Y, or I have to return them, and let's call that variable W, where the Y plus W is supposed to be less than or equal to X. So y plus w is less than or equal to x. So in other words, I sell or I return those newspapers, but y is also less than or equal to the demand. So I'm only allowed to sell whatever the demand is. So the y is the minimum of the demand in x, and then the amount that I return is the maximum of x minus the demand and 0. And then that gives me an equation for the recourse function, which I have here. And then I can just set the derivative of this equal to 0. And I can solve for setting the derivative equal to 0. The solution ends up being that I buy a certain number of newspapers such that the probability of demand up to that point is the profit that I make on sold newspapers divided by whatever I would make on unsold newspapers. So it's the profit on sold newspapers divided by the salvage of unsold newspapers. Okay. All right, so this is what I went through. So I talked about how stochastic programs focus on sequential decisions and realizations of uncertainty. They rely on optimization techniques. There are these different areas: machine learning, statistical decision theory, decision analysis. They all consider similar problems, but they emphasize different things, particularly discovering information, discovering distributions. And stochastic programs can provide, they're fundamentally different, something that you can't get from any single deterministic problem. So that's probably the biggest takeaway, that you can't get a stochastic programming solution from any deterministic problem. And yeah, well, I'll say this one, I think, actually, the next lecture I have more on this, that model value is separate from information value. So the model value is what's the value of solving the stochastic program, whereas information value is the value of learning about the uncertainty and how much you would pay for, maximum you would pay for learning about the uncertainty. So those are two different things, and often they can be of completely different magnitude. Okay. So thanks, and yeah, so next one I'll get more into this issue about the model value and about creating these models for stochastic programs.